We are continuing on here, chapter 18. Yeah. All right. That's right. That's good. We talked about nuclear chemistry last time. And a reminder, as we talked about with nuclear chemistry, um, these type of reactions are different than chemical equations or chemical reactions. As in chemical reactions, we only deal with electrons, but here we deal with everybody in the nucleus, pretty much protons and neutrons. So unlike sort of normal chemical reactions, nuclear reactions, we really don't have conservation of the elements, and that's because we're changing protons to neutrons, neutrons to protons, and a bunch of other things. So that is a very different sort of process that's occurring here. We talked about some different radioactive type particles. There's the alpha particle, which can be abbreviated one of two ways, either with the alpha symbol, 4 up on top, which is the mass number, 2 on the bottom, which is the atomic number. We could also have a beta particle, which also has a couple of different abbreviations. It can use the beta symbol, or it can use an electron or E. Not to be confused with its friend, the positron, and that is like a positive electron there. And that has a positive one, does use the same symbols. We also do some things with a neutron. In addition, a proton as well, which does also roll with a couple of different sort of symbols. So these symbols are widely used in nuclear chemistry. And when we balance, which I think is where we kind of laid it up last time, when we balance nuclear reactions or equations, really there's two things that we're looking to do. We're looking to make sure that all the mass numbers on the left-hand side of the arrow pretty much add up to all the mass numbers on the right-hand side of the arrow. And we also want to make sure that all the atomic numbers that are on the left-hand side of the arrow add up to all the atomic numbers on the right-hand side of the arrow. So remember, as we talked about, since the atomic number is the number of protons and it does tell you the element, that's usually a really good place to start with if you're trying to figure out what's maybe missing. And then you can fill in your mass number. Remember, if there is a coefficient in front of something, you do need to multiply both the mass number and the atomic number by that coefficient as well. A couple of terminology that we talked about: if it goes through some type of decay process, then that particle ends up on the product side. If it does type of emission, that particle also ends up on the product side. If you do some type of bombardment or some type of capture, or bombardment, those particles are on the reactant side. Any questions on that there? So let's take a look. We did one at the end there, so let's do a few more. So why don't you practice here, write the balanced equations for each of these here and see what you come up with. Okay, let's take a look, see how you're doing. So we'll start the first one, alpha emission. Again, that means my alpha particle is going to be on the product side. You again could use helium, or you can use the alpha symbol if you like, whichever one you like. That's uranium. Remember, when it's written like that, that is the mass number. And I know that because I go to periodic table there and find the atomic number, which is 92. So we'll go uranium 238 and 92. Here are missing sort of numbers going to be 92 minus 2, which is 90. That's the atomic number. Go to periodic table, number 90 there, TH. Up on top, I got a 238 on the left and 4 on the right. So if I subtract that, it's going to leave me a 234 left over. And there it will be. Any questions on that one there? Same deal on the next one, beta emission. So emission means my beta particle is going to be on the product side. You can use the beta symbol. You could also use an E for the electron if you like. And again, my neon here, mass number 24, atomic number there from the periodic table 10. Kind of work the same way in this case. This is, though, a negative one, and that is a 10, which means we actually need to go to 11 in this case. 11 plus -1 is 10 on the right. That gives us 10 on the left. 11 would be our friend sodium from the periodic table, and 24 on the left, 0 on the right. It's going to give us 24 there on the right-hand side. Looking at our next one here, positron emission. That again is like a beta particle, but positively charged. So can use the same symbols. Also, again, can use the E if you like. 13 up on top. Periodic table tells me 7. I missed that terribly on that circle. Is our atomic number. Here's 7 plus 1 or -1 is going to give us 6 for our missing atomic number. And number 6 on the periodic table there is carbon. Up on top is going to be 13. Questions on that one there. Lastly, beryllium has an electron capture. So an electron capture means reactant side is where we want to put that particle. And our beryllium 7, and go to periodic table there, 4. In this case, we just need to add them together. So 4 plus -1 gives us a 3 for the atomic number. And that's going to be lithium. And up on top is going to be a 7 there. Any questions on balancing nuclear equations? Not too bad. Just make the final all that, I suppose. No, I'm just kidding. All right. All right, then we're going to then talk about a little bit about stability. And one of the ways that we could look at stability of a isotope is through what's known as the N to Z ratio. That is basically our neutrons. Z is the atomic number, which is basically our protons, right? So basically our neutron to proton ratio. And if the N to Z ratio is too high, the neutrons are converted to protons via a beta decay. And if the ratio is too low, protons will be converted to neutrons either through two methods, a positron emission or an electron capture. And not as efficient, you could use an alpha decay. For us in this class, we will roll with one of these two if it is too low. We will see shortly there is this, what is sometimes referred to as the belt of stability or the valley of stability. And when we talk about too high or too low, we're talking about either the ratios above the sort of the valley of stability or belt of stability, or it is too low. Now, for it being too low, we could either do a positron emission or an electron capture. And the reason you have both of those options is they will give you the same thing. So for example, if we go back to the one we just did there, which was a electron capture, if we did this as a positron emission, we would have 7 for beryllium. Positron emission would be on our product side here. And that would give us our 3, 7, and lithium. So you can see either one of those are going to give you the same product in this case. That's why you have kind of either option on that way. So too low positron emission, electron capture. And that will kind of bring the ratio back up to a more stable situation. Will it make it perfectly stable? The answer is no, but it may in certain cases, but it will at least move it in a more stable sort of arrangement. And if the ratio is too high, it will kind of bring it back down to a more stable arrangement. How do you know what is sort of considered stable or not stable? As I mentioned before, there is this valley of stability, and some books will call it the belt of stability. And for elements that have an atomic number of 1 through 20, a stable ratio is 1. And if you have somebody between 20 and 40, your ratio moves to 1.25. 40 to 80, you're going to move to a 1.5 ratio. And really anything above 84 is not going to be stable. So, you don't have to worry too much about that. Now, for us, I'm going to say we're going to use these as sort of hard cutoffs. So if it is somewhere between 1 to 20, it needs to be 1. If it's really kind of 21 to 40, we'll do 1.25, and 40 to 80, or really 41 to 80, we'll do 1.5. What I mean by that is you can see this number is 20 that ends it, this number is 20 that begins it. So there is sort of a grayish area. Sometimes the books will go, well, it's kind of that grayish area between the two, so it's okay, it's still stable. So to take that out of it, we're just going to go these as hard cutoffs, but just know in a book sometimes they won't do that because there's sort of that grayish area between one and the other where they kind of blend together. And I won't give you one on purpose in the cutoff region there, so it'll be either clearly above or below the cutoffs of those guys. All right, so let's give it a try here and see. Why don't you predict the kind of radioactive decay that magnesium 22 will undergo? Magnesium is number 12 there, yeah. So write the balanced nuclear equation for what's going to happen here if it is not stable, which based on the question, I feel like it might not be stable. Yeah. So first thing we want to figure out is our ratio here. So again, the 22 is the mass number, atomic number there from our periodic table. N to Z ratio is basically our neutrons to protons. So obviously Z is going to be 12 in this case. Now our neutrons is again our mass number, which is 22 minus our atomic number, which is 12. That is 10. So our N to Z ratio here is going to be 10 divided by 12, 0.8, a bunch of threes. This has an atomic number of 12, which puts it between 1 to 20. And the acceptable stable ratio is 1 in this case. So in this case, we are a little bit low here from our belt to stability. So because we are low, this is the one where we have kind of two options to bring that ratio up. We can either do an electron capture, or we could do a positron emission. So again, here, if we did either one, we would take our 2212 and magnesium. We did an electron capture. It looks something like this. Again, capture of our electron on our reactant side. 12 and minus 1 is 11, and 22 up on top. Number 11 from the periodic table is sodium. And we can also do our positron emission like we just saw in the last example. It will come out the same here. So again, our missing number is 11 and 22 sodium. Now, in this particular case, we could do either one. What we do end up with now is sodium 22. And if we look at the N to Z ratio of our sodium 22, that's 22 minus 11 gives us 11 neutrons. And we obviously have 11 protons. So in this case, 11 divided by 11 is an N to Z ratio of 1. We definitely have brought it up from where it started at 0.833. We actually brought it up perfectly stable now, right? So we hit something that's actually pretty stable at this point with that ratio of 1. This will not always be the case. So you may do this kind of emission or whatever it may be, and you may not hit perfect ratio, but it should move you in the right direction. So again, because we're lower, we definitely, if we don't hit that perfect ratio, should move us in the direction of that. Any questions on that one there? All right, why don't you try this one? Krypton 85, same deal. Stable, write the reaction. What do you get? Krypton is 36. We'll start with our numbers. So we got 85 for our mass number. Again, from the periodic table there, 36. That means our proton's going to be 36. Our neutrons here are going to be our mass number minus our atomic number. And that's going to get you a 49, looks like. So to calculate our N to Z ratio, we'll take our neutrons, which is 49, divided by our protons, which is 36 in this case. It's going to give us a 1.36 ratio. Since this does fall between 20 and 40, the acceptable ratio is like 1.25 in this case. So to me, that looks a little high in this case. So it will go through a beta decay to bring it back down. So if we were writing that reaction here, we would have our beta particle on the product side. That's 36, and -1 means we actually have to go 37 on the periodic table. 37 on the periodic table, little rubidium Rb, and up on top is going to be an 85 in this case. Once again, if we look at sort of the ratio here of what was just made, we have 37 and 85 minus 37 is 48 in this case. Divided by 37 gives us a ratio, we'll call it 1.30. Not perfect, but it is, again, moving in the correct direction here. It's moving towards that 1.25. And that, again, is sort of the goal of this reaction here. Yeah. In reality, things usually do continue kind of to decay once they kind of start in a lot of cases and continue until they hit something that is stable. For the purposes of this sort of problem, you usually just need to write the one equation, even though, again, it doesn't get perfect. And usually that should be sufficient. Other questions? All right, let's see here. So that is one popular way to think about stability. There are some other things besides the neutron to proton ratio that we could look at in terms of stability. We'll talk about a couple of things here. One of the other big sort of factors in terms of stability is the number of protons and neutrons. And just oddly, an even amount of those things are really good in terms of stability. So as you can see here from this table, and you have a similar table in your book, but if you have even protons and even neutrons, there's about 157 nuclides that are stable in that sort of arrangement. So that's sort of like your best arrangement. The next sort of best arrangement is even protons, odd neutrons, still about 53. Next best, odd, and then even, you got 50. So they're kind of relatively close. If you got one at least even in there somewhere, you're still not too bad. Worst case scenario is, as you can see, they're odd of everybody, right? Only about 5 of them are stable in that sort of arrangement. So that's also a very quick way. Sometimes people look at stability is, do we have even protons and neutrons, or at least something that's even? And I sort of give you an idea of that. In addition, the total number of nucleons, and nucleons is a word that you hear a lot in nuclear chemistry. It pretty much means what's in the nucleus. And in the nucleus is protons and neutrons. It's kind of like a fancy way of saying mass number, I suppose, in that case. So it's basically what we talk about nucleons is the number of protons and neutrons, stuff that are in the nucleus. So if you have sort of a certain numbers that add up to what are referred to sometimes as magic numbers in the nucleus is more stable. So if we have either N or Z that has 2, 8, 20, 28, 50, 82, and your Powerball number of 126 there for neutrons. These are sort of like hitting like noble gas configuration in terms of stability with electrons, and they're sort of considered a nicely stable type situation as well. So again, a lot of times the N to Z ratio, even odd protons, neutrons are two really things that we look at a lot in terms of stability. Now, speaking of sort of a question that was asked a second ago in terms of do things kind of continue on until they hit something that's stable, and a lot of times in what is sometimes referred to as a decay series. In a decay series, you have just a bunch of basically radioactive equations or reactions happening one after another until, again, you kind of hit something that's sort of stable. The beginning person is sometimes, again, referred to as the parent nuclide, and the daughter nuclei are those guys that are sort of produced as a result of these things. Now, if you want to count the number of alpha and beta particles, there's sort of a quick way you could kind of get to the end product if that's all you're interested in. So for every alpha decay that it goes through, you're going to subtract 4 from the mass number and 2 from the atomic number. And for every beta, you actually will add 1 back to the atomic number. And that would be a situation maybe you just want to kind of get to the end and see. So, for example, if we take a look at uranium-238, let's just say we had uranium-238, 238, I'll spit that out. And again, obviously from the periodic table there, we could get 92. And let's just say it did, we'll just do a few of those there, like, we'll do, let's just say it went through alpha, beta, beta, alpha decay, and maybe more, but we'll just stop at those 4. So if you want to know sort of what's happening after each of these sort of decay processes, there's really 2 ways that you could do it. I'll just clear out some room here. You could just do it like we did with balancing equations. And what you would do in this case is the first sort of decay process is going to be an alpha decay. So you would just write a normal sort of nuclear reaction. Here again, our 92 on the left and 2 on the right. That gives us our 90 that's missing and our 238. Now our 234 there. If you actually subtract it. And that's going to give us TH here, 234. Now, what happens in this sort of decay series is what you produce here will then be the starting of your next step. So this guy here that was produced in the first decay process will now be sort of our starting process here, as this guy will now go through a beta decay. And that's going to be a 0 minus 1 here. And again, we would have to go 91 in this case, and 91 is going to be PA and 234. This guy again will now be your next starting guy in this series here. And next one is a beta, so we'll do a little beta action again. We're going to have to go 92 on this, which is going to bring us back to uranium, and a 234 in this case. And lastly, in this very short little decay process here, we're going to take that guy and then hit it with a alpha at the end. And that's going to get us here to 90 and 230. And again, 90 is going to be TH in this case. So if you want to do a decay series and you want to know, again, what you get after each step, you basically just do your balancing your nuclear equations like we did previously. And whatever you produce on the first step becomes the starting on the second and so forth. Now, if you were maybe just interested, say, in what you get at the end of the process here, since they're all alpha and beta, you could do this. You could go 238, your 92 uranium. And we have, in this case, 1 and 2 alpha decays, which means we're going to subtract -4 from our top one, -2 and -2 from our bottom. And we have 2 betas, which means we're going to add 1 for each of those to our bottom. That's going to get us a total of 230 up on top. 238 -4 is 230. 92 minus 2 is 90, minus 2 more is 88, plus 1 is 89, plus 1 more is 90, and that just gets us to our end product here. So if you're just kind of interested in what's at the end, and again, it's all alpha and beta sort of decays that are happening, you could just mathematically do that and adjust either the mass number or the atomic number. Any questions on that there? Okay. So as you can see here, this is uranium-238, and it actually kind of breaks off after a point here. It then kind of separates one way or the other. They all hit, though, there at the end, which is stable lead right there. Lead 206 is where they all go. So in a decay series or process, it will continue this sort of natural decay process until it hits something that is a little bit more stable than where it started with, and it will kind of stop at that point. So let's talk a little bit about kinetics and radioactive decay. And all radioactive decay follows first order kinetics. So first order kinetics is the same first order kinetics you talked about in 200A for like 10 minutes probably. So we'll talk a little bit about it here. When we talk about first order kinetics, there are really two sort of important equations that go with it, and that is what is sometimes referred to as the integrated rate law, and that is the natural log of A is equal to the natural log of A naught minus KT. This is, you could think of it like your final concentration. This is like your initial concentration. This is what we call in kinetics the rate constant, but here in nuclear chemistry, they like different words. So that is known as the decay constant, kind of the same thing. This is actually time and not temperature. So that little t there is actually time in this case. There is a half-life equation that goes for first order kinetics, which is the natural log of 2 over the decay constant or the rate constant. And that is actually where this number comes from. If you take the natural log of 2 on your calculator, you get 0.693 divided by the rate constant here. So that is where that comes from. Now, these guys are sometimes used differently, and this is just a mathematical arrangement of the natural log of final over initial, or in this kind of case. And they also will sometimes use, instead of A, they'll use N for nucleides here. So sometimes they'll use N in place of there. And some books will actually use lambda instead of K for the decay constant. Because they are nuclear chemists, they like to use some different symbols, which means the same thing. So that is the decay constant. So if you see lambda, sometimes they'll use that instead of K. And again, T here is still time in this case as well. Now, the half-life is, as you may know, the time it takes for half of whatever you started with, obviously, to go away. The shorter the half-life, right, the quicker it will basically go away and decay. The longer the half-life, it will stay for a long time. One of the things, if you remember kinetics, is they like graphs a lot, and the common graph that you see for first order kinetics is really the one over here. And if you take that first order equation and take the natural log, and I'll use the A, is equal to minus KT plus the natural log of A naught. This is written in the form of y is equal to mx plus b, the equation for a straight line. So on the y, we graph the natural log of A, basically. On the x, we do t. That will actually yield you a straight line, a linear relationship, where the slope of this line is equal to minus the decay constant or the rate constant. And that's because the line there is a negatively sloping line. And that negative plus this negative will turn your rate constant or decay constant into a positive number. Now, when we talk about the decay constant and stuff like that, typical units are 1/seconds or reciprocal seconds, but honestly, they can be anything like 1 over a unit of time is typical units. They could be 1/minutes, 1/seconds, 1/years, 1/days, but anything kind of reciprocal unit of time is the typical units that you see with the rate constant or decay constant, if you want to call it that. Now, these two equations are oftentimes used together. And especially in this chapter, they are very fond of giving you the half-life, but not giving you the decay constant. So a lot of times what you have to do is use the half-life equation to get K, and then stick your K into this equation, actually solve for the problem for what it's looking for. So that is a really common sort of thing that you have to use both of these sort of formulas together. And in most cases, that's what you would be doing. You'd be given the half-life, use that half-life equation to get the decay constant, put the decay constant to the integrated rate law and solve for something like maybe time or a concentration. Speaking of units and time, it is super important when you use this equation that these two units our values have the same unit of time. And that's also a very common thing that's different. Sometimes you may be given your decay constant or half-life in years or something like that. and maybe your time is in like days or something like that. So you want to make sure that unit of time is the same in both of them. It really doesn't matter which one you convert it to, as long as they are both the same when they go into that integrated rate law. Otherwise, well, frankly, you'll get the wrong answer. I think it's not what you want to do there. Now, when we talk about half-lives, as I mentioned, that's the time it takes for half of whatever you start with to disappear. And half-lives can be really, really short or super long. So you can see there, uranium-238 that we're just looking at has a half-life of 4.5 times 10 to the 9 years, which means probably none of us will be around for one half-life, right? So I don't think. Carbon-14 there, 5730. Closer of a shot, maybe. But here you can see, obviously, we got some seconds, so maybe we can make those, I suppose, as well. Obviously, these can be used in different things. We'll talk about a little bit later on in the chapter. If you're doing something with medicine, clearly a shorter half-life would probably be preferred. Otherwise, your follow-up appointment is going to be a lot of years down the road, right? So you usually want to do some type of small one there. And obviously, things, for example, as we'll also talk about, like fission reactions that use uranium, they produce things that obviously has a half-life for a very, very long time. And that's all the issues of where do you store it, who keeps track of it, right? So these things are around for a really, really long time. So why don't you give one a try here? And by the way, in those sort of kinetics equations, even though we typically in kinetics use molarity, you could actually use just you could use for these, even though a lot of times in kinetics we use molarity on both sides, you could actually use any unit you like here. You could use grams on both sides, milligrams on both sides. You could use a rate of radioactive decay on both sides. So as long as the units of whatever is going into here and here are the same, you're good to go. It doesn't have to be a specific unit or anything like that, even though a lot of times in real kinetics we use kind of molarity. So why don't you give it a try here? If you have 1.35 milligram sample, plutonium-236, calculate the mass that will be there after 5 years and the half-life here of plutonium in there. Okay, since we're getting that, let's take a look at this example here, just to finish up this one here. Obviously, it's a no-brainer here. If it is radioactive decay, it's first-order kinetics. So really, these are always going to be the formulas you're going to use. And again, our half-life here, natural log of 2 divided by k. In this particular case, it did give us the half-life. We do have our time, which is 5 years. We have our initial, which is 1.35 milligrams, and we're actually looking for our final in this particular case. So you hopefully can see that the one other thing that you're sort of missing to be able to sort of solve it is the decay constant. And that would be why they did give us our sort of half-life here. We could then get our decay constant and put it in there and solve for what we need. So we'll start with that. The half-life here is going to equal our natural log of 2 divided by our decay constant. That is 2.86 years. These guys basically just switch places on the exchange there. And that's going to give us the natural log of 2 divided by 2.86 years. That is going to give us a decay constant of 0.2426. The units here are reciprocal years, or 1/years in this case. Again, obviously, this guy's going to go to the bottom, so our 1/years. Now we are good to go. We can put it into our equation here. Natural log of what we're looking for is equal to our natural log of our initial, which was 1.35, minus our decay constant, 0.2426 reciprocal years, and our time, which is 5 years. So this is what I was talking about earlier. I got years there and years there. That's good. It's going to cancel. That's not always the case. So you got to watch those units on both of those. But in this case, we're good. Those guys are going to cancel correctly. All right, cleaning up the right-hand side, I think, 0.2, we'll take that guy times 5. And we're going to take the natural log of 1.35 minus, basically, I think you get something like 1.211795 minus that. That's going to give us a natural log of A is equal to negative 0.91169. to get rid of the natural log, you need to take the e of both sides. Yeah. When you do that, that gets rid of the natural log on that side. That gives us a concentration of, this should be larger or smaller than what we started with. Should be smaller. If you end up larger, you maybe went the wrong way. This is milligrams in this case. And we end up with 0.402, which is obviously less than what we started with. Question on that one there. All right, we're going to let it up there for now. Okay, we're going to continue on here, and why not? So let us continue on with this example. So once you give this one a go, see what you come up with. We have radon 22. It's a gas that causes lung cancer. Cheerful. And this produced by uranium decay. If we have 10.24 grams of it in the house today, how much will be there in 5.4 weeks? Radon 222, half-life 3.8 days. See what you come up with here. Okay, so let's take a look. So in this case, once again, definitely going to roll with our equations here for first order. And our half-life equation. All right, so we got something here. Assuming again, there are initially here 10.24 grams. We want to know how much will be there basically in 5.4 weeks. So we're looking for A basically in this case. And they gave us the half-life here of 3.8 days. So once again here, we are kind of short our decay constant to solve for what we're looking for. I do see, as I mentioned before, some issue here with our units. So again, at some point, those units need to be the same. It doesn't really matter which way you go. You can take the weeks to days, days to weeks. It will come out the same at the end. I'm going to, in this case, actually just convert my days into weeks. So I'll just do it up front here. So I think there's 7 days, they say, in a week, I suppose. Yeah. And that's going to get us here 3.8 divided by 7, 0.5426 weeks here. All right, so now using my half-life equation to solve for my decay constant, that's going to equal 0.5426 weeks. Again, these two guys basically just switch places. So we're going to take the natural log of 2 divided by my number there, my 0.54 number. And that's going to give me a decay constant of 1.27. I'm going to take a few digits, 69. These are going to be reciprocal weeks, or 1 over weeks here are the units. Any questions on that there? At this point, we now have K that's actually in the same units as my T. So we should be good to go to pop it in here. So that's going to be the natural log of 10.24 grams minus my K, which is my 1 point, I get there, 2769 weeks. And I'll move that out of the way maybe. And we could do our time, which is also in weeks, so everything cancels correctly. And it was 5.4 weeks in this case. Weeks are going to cancel. My final units here are going to be in grams like the original. We'll go 1.2. Actually, we'll just take the whole number there times 5.4. That's going to give us something on this back end of 6.894. And we'll take the natural log of 10.24 minus that number. And that's going to give us a natural log of A is equal to minus 4.56869. Again, we're going to E both sides there, and that will give us a final sort of concentration here of 0.010 grams in this case. Any questions on that one there? Again, if you took the weeks to days, you'll have some different numbers, but the end result should hopefully be the same at the end. Yeah. Any questions on that one there? So again, very common now to use both of those together, especially in this chapter, and because they like to give half-lives of things. So a lot of times using it to get your decay constant. All right, that was that one there we just did. Hopefully they got something like we got there. Now, we could also use radioactive decay to basically figure out how old something is through radiocarbon dating, for example. Radiocarbon dating is 5730 years is the half-life of carbon-14. And you could also figure out the ratio basically of how much you have here for lead versus how much you started with of uranium. And you could also figure out how old something is. It's still really going to be first order kinetics. The difference here is sometimes we will use rates of radioactive decay here to kind of solve for it. So let's take a look at one here together. So an ancient skull gives a reading of 4.5. That's disintegrations per minute per gram of carbon. So that's not Celsius in this case. So that's actually per gram of carbon. The per gram of carbon is important because it tells us basically we want to use the half-life of carbon-14 here when we're using our equation. If a living organism gives 15.3 disintegrations per minute per gram of carbon, how old is the skull? So again, we could use our half-life here of 5730. Again, because of the carbon here. So in this case, we're still going to use our same equation. So we have our natural log of A is equal to our natural log of A naught minus KT and our half-life here. Natural log of 2 over K. Here we have our initial, which is our living thing, all right, 15.3 disintegrations per minute per gram carbon. Our final, which is the dead thing, I guess, 4.5 disintegrations per minute per gram of carbon. And we want to know, in this case, T, how old is it? So once again, we do need to use our half-life equation to get to our decay constant so that we can actually solve for time in this case. So using our half-life equation there, which is equal to 5730 years, is equal to the natural log of 2 divided by K. K would equal the natural log of 2 divided by 5730 years that they switch places. That's going to give us a decay constant in this case, if I hit the right numbers, of 1.21 times 10. That's a lot of zeros. 1, 2, 3, 4. Not a lot, I guess. Reciprocal years here. Now that we have that, we're going to go natural log here of 4.5. Once again, this is a rate of radioactive decay, and we can use it in this equation just like we use grams or molarity or whatever you want to use, as long as both of these guys are basically the same units. So as long as these are the same units, you could go into this equation with no problem. Minus our K that we just calculated there, 1.21 times 10 to the minus 4 reciprocal years, and our T. We're going to solve for T. I personally would take the natural log of this guy and then subtract it to the other guy. So here I would take the natural log of 4.5 and subtract it from the natural log of 15.3. And if you do that, you're going to end up with, if I can find my pen, negative 1.2 through 238 equals our negative 1.21 times 10 to the minus 4 reciprocal years. We're going to then divide this to the other side. There is a negative that comes along with that, which will then make our time positive, which is good. And that's going to give us roughly here, go this way, it's probably easier for you to see. Time's going to be 10,114 years. And if you want to clean it up to about 3 sig figs, about 10,100 years in this case. So kind of old in that case. Yeah. Any questions on that one there? All right. And by the way, the units for these guys actually cancel because, again, that relationship of one divided by the other, that's where how those units basically go away in that case. All right, why don't you try one then? Why don't you do not this one, since that's the one we just did. All right, archaeologists have dated ancient civilization 15,600 years. If a living sample gives 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon if you found a grain of rice on the site there? Yeah. So again, since it's grams of carbon, we'd be using the same half-life as the previous problem. And our half-life equation in case we need it. So in this case, we are actually looking for A. We're looking for kind of the final counts per minute. We have our initial, which is 20 counts per minute per gram of carbon. We have our time, which is 15,600 years. We again don't have K, so we could use our half-life equation. Since we're using really the same ones we did in the previous problem, K will come out the same here. So that was our 1.21 times 10. Was it -4, I think, right? If I'm not mistaken. -4 years. So you should get rid of the same K as we had in the previous problem, as obviously it's the same half-life. So with that being said, we then can go into our equation here, natural log of A, which is what we're looking for, natural log of 20 minus our 1.21 times 10 to the -4 reciprocal years, and our 15,600 years. Here, in terms of units, we're okay as they are both the same. So we don't have to do any type of changing. So if we kind of clean up this side here, we will end up with something. 15,600. Looks like 1.8876. So natural log of A would then be equal to the natural log of 20 minus that number, and that's going to give us a 1.10813. We're going to E there both sides. That's going to go away, and that will then give us here 3.03 for our A. The units here are going to be the same units as our initial, so it's going to be a rate of radioactive decay, counts per minute per gram of carbon would be the same units as our initial. Question on that one there. So again, all radioactive decay, anything to do with that is basically first order, those two equations, probably use them together. Any question on kinetics here involving radioactive decay? All right. I think they even got the same answer. That's good. All right. All right, so now we're going to talk a little bit about where the energy from fission comes from. And a reminder, I think we talked a little bit about fission last time, but got the right pen there. Fission is basically the idea where you do have a unstable nucleus, and that can occur naturally. It could also occur by you, again, shooting something out of it. We might have talked about last time as well that makes it unhappy. It will typically go through a fission reaction where it will make basically two new nucleuses here. It also will usually release some neutrons, maybe a number of neutrons. And it also will release a good amount of energy in that process. And fission reaction is the reaction used in things like a nuclear power plant and so forth. So during the nuclear fission process, some of the mass of the nucleus is actually converted into energy via this equation here. That's not negative. That is Einstein's equation, equals mc squared. And E is equal to mc squared, c being the speed of light. I'm going to roll with 3 times 10 to the 8. I know some are fond of 2.997 times 10 to the 8, but it seems like a lot of numbers there. We're going to go with that. And m here is really the mass, or as we'll talk about in just a second, in this sort of application, it is the mass defect of the situation that's happening. So each mole of uranium-235 that goes through fission produces about 1.7 times 10 to the 13 joules of energy. In comparison, if you took a very exothermic chemical reaction, you're just generating about 10 to the 6 joules of energy per mole. So this is why, again, it's used in some things like nuclear power plants. It generates a lot of energy that can be used, obviously, to send power there in the plant by basically heating up the water. Now, the mass defect is actually the difference between the mass of the nucleons, or the particles that make up the nucleus, which is basically your protons and your neutrons, and the mass of the isotope that is formed. There is this slight difference that does get sort of converted into energy, this mass, and that's what's known as the mass defect. That is what is in Einstein's equation, the m, in this application. And that is basically the mass defect in this particular case. Now, binding energy, nuclear binding energy is basically the energy that's sort of released when, one of two ways, depending on how you look at it, either when you make a nucleus or when you basically break apart a nucleus. So one of two ways. The number is actually the same. The difference is the sign. One's negative or one is positive, being endothermic if you need to break somebody apart, right? Exothermic if you're going to put it together. So again, you'll get the same binding energy value, but sometimes you'll see a negative or a positive depending on sort of what you're talking about, either kind of putting it together or kind of breaking it apart. Now, there are some, dare I say, shortcuts to the Einstein equation, which are some constant sort of conversions that are sometimes helpful. And these are a couple there on the bottom. 1 mega electron volt is equal to 1.602 times 10 to the minus 13 joules. And 1 AMU, a mass defect, is equal to 931.5 mega electron volts. So common units of binding energy is one of two sort of units. It is typically joules per nucleon, or mega electron volts per nucleon. And these are two very common units of binding energy. Nucleon, as I mentioned before, are our protons and neutrons, as we talked about, basically what's in the nucleus in this case. Binding energy, as we will talk about, is also a measure of stability. And depending on the binding energy you have per nucleon will give you an idea of how stable something is as well. So let's take a look at an example here. Let's say we had a fluorine isotope here that had an atomic mass of 18.9984 AMU. And we wanted to calculate the nuclear binding energy. So let's go through this together, and we'll look at it a couple of ways that you could do it. And then you could kind of choose, I suppose, whichever way you want to do it. So the first thing that we want to figure out is the mass defect. And the mass defect, again, is the difference of our protons and neutrons, which are what makes up the nucleus, and the mass of the actual isotope itself. Now, again, this has 9 protons because the atomic number is 9, and 19 minus 9 is 10, which is where we get the number of neutrons from. So this is the atomic mass of a proton and the atomic mass of a neutron. And to calculate the mass defect, what we do is essentially take our 9 protons in this example and times it by the atomic mass of a proton. We then add it to 10 times the atomic mass of a neutron. And then essentially what we do is subtract it from the atomic mass of the isotope itself, which would be 18.9984 AMU. And if we do that in this particular case, we will get 9 times 1.007825 plus 10 times 1.008665. And no tangent needed, so I'll hit that button. And then we're going to subtract it from 18.9984. That is going to give us 0.158, I don't know, we'll call it 7 AMU. This is the mass defect. This is the difference in the mass of the nucleons or the particles of the nucleus and the mass of the isotope itself. This is the slight mass that's going to be converted into energy during this fission sort of process. Now, to calculate the binding energy, we can definitely use Einstein's equation, equals mc squared. And if we do that, we'll put in our number here, 0.1587 AMU. That would be our mass defect, which is this guy. We're going to times it by the speed of light, which is a constant. And that's going to get us here, and I'm going to use a non-rounded number here. That's going to get us 47602,500. This is AMU meters squared second squared in this particular case. Questions on that so far here? Yeah. C is a constant. Yeah, that's the speed of light in this case. Now, these units are not really the units that we're perhaps looking for in this particular case. We are looking for some joules, but maybe you'll recognize that it is fairly close. Just to make sure I punched everything right here, 0.1587 times 8 squared. There you go. I feel like maybe I didn't hit it right there. Yeah, I feel like that number just didn't feel right to me either. So let me try that again here. All right, let me just actually punch it in right here. Feel like I missed the squaring part there. So 3 to the 8, actually hit the square button. That should help. All right, we actually get, I'm sorry, 1, not that, come here. Let me something right with 1.428 times 10 to the 16. That feels a little bit better, maybe. All right. Now, AMU per meter squared per second square might look close to something a joule equals. Perhaps you remember a joule equals a kilogram meter squared second squared. Yeah, so maybe remember that. If not, let me tell you, it equals a kilogram meter squared second squared in this case. So we can then take our value that we just got here. Perhaps the right value would be good as well. And we can divide it by a number here, which is 6.022 times 10 to the 26. 26 AMU, right? 23 is grams. Yeah, 26 is kilograms. Yeah. So Avogadro's number to the 26th there is kilograms rather than to the 23rd, which is grams there. Just kind of stops one conversion you don't have to do. That's going to get rid of our AMU, and that's going to turn us into our joules, basically. So we'll take that number, we'll divide it by 6.022 to 26. Going to get us a 2.37 times 10 to the minus 11 joules, and that's because it's a kilogram meter squared second squared, and that equals a joule. We do usually report this as joules per nucleon, so we would divide this by 19, which is our protons and our neutrons, and that would get us per nucleon here 1.25 times 10 to the minus 12 joules per nucleon. Yeah. Any questions on that there? Now, if I wanted mega electron volts per nucleon, I could do a couple of things. I could, at this point, just use our joule to mega electron volt conversion that we saw on the previous page, where 1 mega electron volt is equal to 1.602 times 10 to the minus 13 joules. The joules would cancel, and that was a conversion that was on the previous slide. 0.602 to the negative 13. That would get us something like 7.792 mega electron volts per nucleon. Also another common unit of binding energy. So joules per nucleon are mega electron volts per nucleon is also, again, like I said, common units. First off, any questions on that? Now, if you don't want to use Einstein's equation, you can use some of those conversions that we had on the previous slide, and you could kind of bypass Einstein's equation because those conversions are kind of based off of it anyways. You can get up to this part right here, and you could take the mass defect that we calculated, the 0.1587 AMU, and you could use that conversion on the previous slide where an AMU equals 931.5 mega electron volts. And that would get you a 0.1587 times 931.5, 147.83 mega electron volts. You then can divide it by your 19 nucleons. And you should hit that number pretty close to what we have on the bottom there, with the rounding a little bit different, but basically 7.78 mega electron volts per nucleon, which is essentially this number, just without a little bit of difference in rounding. And then at that point, if you wanted to, you could use the other conversion to go to joules. So if you want to just use those conversions rather than Einstein's equation, you could get the same answer. And again, you could use the one now from mega electron volts to joules, which is the one that we used down here. You could use that, and it will take you over to this guy if you want to go that route as well. Any questions on that there? All right, so binding energy per nucleon, as I mentioned before, is a measure of stability. And as you can see here from this graph, as the nuclear binding energy per nucleon increases, so does the stability. That's going to be our winner right there. Iron 56, quite stable. So that's kind of a really stable guy right there. So this is another measure of stability, like we talked about the N to Z ratio and the even, odd. Binding energy per nucleon, the higher the binding energy per nucleon, the more stable that nucleus is going to be. Here's another picture, and as you can see, either fusion or fission happens, and that brings us to our most stable sort of nuclides in that sort of region in terms of their binding energy. So why don't you try this one here, and there's some numbers you could use. Calculate the mass defect and the nuclear binding energy per nucleon in mega electron volts. Well, we do both, and joules. Why not? Joules per nucleon. Good practice, just in case I decide one over the other when I'm making the test, I suppose. Just have you do it all, I suppose. Radioactive isotope here, carbon-16 has a mass of 16.014701 AMU. Carbon there on the periodic table is still number 6, I think. It's hard to see, but I think it's 6. Okay, let's take a look, see how you're doing. Again, we'll start with protons and neutrons since we need to figure those out. So obviously here we got 16 and 6. So we got 6 protons here, and obviously 16 minus 6 there would give us 10 neutrons. So we need that to get our mass defect. So that's where we could start with here. So our mass defect will be our 6 protons, and we'll use the number they got here, 1.00783 AMU. Going to add it to our 10 neutrons at 1.00866 AMU. And then basically we're going to subtract that from the atomic mass here of our guy, which is 16.014701 AMU. That's going to give us the difference in mass of the isotope to our particles that make it up that will be converted into energy in this case. And it looks like 0.118879, if I am not mistaken, AMU. Again, at this point, you do have a couple of options since we're looking to solve for it each way. You can, like I mentioned before, kind of bypass the Einstein equation and just use our conversions that we got going on. So we'll go that way here to get to our mega electron volts. So 1 AMU is equal to 931.5 mega electron volts. The AMU will cancel. And we will go 931.5, going to give us about 110.7 mega electron volts. We then can divide it by our nucleons, which is 16 in this case, which is our protons and neutrons, basically our mass number. Divided by 16, going to get us a 6.921. And this is mega electron volts per nucleon. We can, at this point, also just use a little conversion. I feel like I lost me a number there. Maybe I did 921. No, I didn't. 921 mega electron volts per nucleon. And we could use mega electron volt 1.602 times 10 to the minus 13 joules, which is that other conversion that was on that previous slide. And that's going to get us a 1.11 times 10 to the minus 12 joules per nucleon. Yeah. Any questions on that? You obviously could have equals MC squared it, took your 0.118879 AMU, your 3 times 10 to the 8 meters per second squared. Once you get that number, a little Avogadro's number to the 26. And that would get you your joules. And then you can divide it by the nucleon and obviously continue on to mega electron volts if you wanted to. Any questions on that one there? All right, one last little mass defect problem here, a little iron action, hopefully. There it is. Calculate the binding energy per nucleon of iron 56. Let's see what you come up with here. We'll do it at from the periodic table is 26, I hope. So we got a little iron 56, 26. So 26 protons, again, subtracting top number from bottom gives me 30 neutrons, I believe. So we'll start with our mass defect here. And again, we'll go 26 times our 1.00783 for our protons plus our 30 times 1.00866 for our neutrons. We're going to subtract that from our molar mass or atomic mass of our isotope, 55.93494. This is going to give us our mass defect. Again, that difference in the mass of the particles and that of the isotope itself. And it looks like we will yield here. A mass defect of 0.52844. Since we are looking for mega electron volts in this case, I'm just going to use the conversion here. 52844 AMU. Again, an AMU is equal to 931.5 mega electron volts. So times 931.5, going to get us a 492.24 mega electron volts divided by our nucleons in this case, which is 56 nucleons. And if we do that there, that's going to get us an 8.79 mega electron volts per nucleon. Obviously, if you wanted to, you could convert it to joules, but that would be it there. Question on that one there. Now, in comparison here to the three that we calculated, this is our iron. We did carbon previously, 6.921 mega electron volts per nucleon, and that was carbon. And we did fluorine at the very beginning, ended up something like this. And what we can see here is the iron 56, like we saw on that graph, was at the top. It is the most stable based on binding energy per nucleon. Out of these three, this would be the least stable of the three, right? It was just the smallest binding energy per nucleon. Any questions on that there? Yeah. I will, yeah. So you'll be given really this, this, and the joule one as well. So I would recommend going that route. Then remember, E equals MC squared. But if you want to use that, you can. It works as well. Yeah. Other questions? All right, we're gonna lay